Hi, grade 11 chemistry class. Welcome to another installment of your video chemistry lessons. Today we'll be focusing on the calculation of percent yield in chemical reactions. Okay, thank you for watching. Okay, with percent yield, sometimes chemical reactions, they don't yield as much as you would expect them to yield during an actual laboratory or field study because it's just the fact of life. For example, here, if we have an example of equation like this one, 2 moles of A, it gets together with 3 moles of B, and it should yield 1 mole of C plus 3 moles of D. Okay, this is a hypothetical situation. In fact, most often in real life, you won't get your full 1 mole of C, you won't get your full 3 moles of D. That's a fact of life. And so we try to quantify how much we actually do get using this thing called percent yield. So here are some definitions to help us through this. So a chemical reaction's theoretical yield, it's the amount of product that is predicted by stoichiometry. For example, in this equation here, as long as we had 2 moles of A and as long as we had 3 moles or more of B, then we should end up with 1 mole of C and 3 moles of D. Okay, that would be the theoretical yield, is these products here. But an actual yield is the amount of product that is actually measured after the reaction took place in the lab or what have you. So for our example's reaction, the actual yield would likely be a little bit less than the 1 mole of C, and we'd have a little bit less than the 3 moles of D. Typically, that's the way that it works. Why? Okay, so we can start talking about that now. First of all, there are things like competing chemical reactions taking place in the real world, in a laboratory. So for example, if we were combusting propane and we were expecting that it was a complete combustion type of reaction, then here's the chemical formula or chemical equation that we'd be expecting to take place. So methane is forming carbon dioxide and water because of its reaction with oxygen. That's what we're expecting to happen, and that would yield a theoretical amount of each of the products. However, as that complete combustion is taking place, we have to recognize that there's also incomplete combustion happening at the same time. So some of that methane is being drawn into equation B here away from equation A, and that's going to result in the production of some carbon monoxide. So some of that carbon is going into carbon monoxide, so the yield of carbon dioxide will therefore be less than was originally expected. Okay, so that's just with the combustion. Here's another reaction that we can use as an example. Phosphorus and chlorine get together and should yield phosphorus chloride. Phosphorus trichloride. And so we expect that to happen, but as that happens, some of that phosphorus trichloride is having a second reaction with chlorine and forming a little bit of phosphorus pentachloride. So some of the phosphorus and some of the chlorine from the original reactants are being used up to make some of this stuff when we were expecting it would make that. And so our stoichiometric calculations don't seem to make sense, and it's because there's this competing reaction happening. Okay, reaction D is the competing reaction. Also, we have to consider the fact that there are differences in the rates of different types of reactions. So some reactions will happen so slowly. If they are slow, you're going to end up with possibly a situation where the reaction does not complete 100%. Okay, so if the reaction does not complete 100%, for example, if we're looking at reaction C here, maybe when we put in 2 phosphorus, we won't get a full 2 moles of phosphorus trichloride because the reaction was just so slow, it didn't go to completion. Okay, that's another reason why you may have a percent yield. Laboratory techniques for collecting products. So when we collect products, we have to recognize that sometimes, because of the techniques we're using, some products get left on a stirring rod, or some products get left in another piece of apparatus. Maybe it's not fully measured correctly. It could be any number of reasons, but laboratory techniques can definitely affect the percent yield. impurities in the reactant. So if we're not using pure phosphorus, for example, if we're not using pure chlorine, then we're going to mass the reactants in advance and think that we have lots of phosphorus, lots of chlorine, when in fact we don't. We've got a bunch of other things thrown in there and we'll get less of our product. So impurities in reactants will also affect the percent yield. So now that you understand what percent yield is all about, here's how we actually calculate it, okay? This is the equation. So percent yield is basically the actual yield, what we've taken maybe as a mass in our laboratory, and divide that by the theoretical yield, or the amount of mass that was predicted by stoichiometry. So we divide those two things, and we're basically getting a ratio. We multiply that ratio by 100%, and that gives us our percent yield. Okay, here's how the percent yield would work in an actual problem. We've got an example problem right here. So 2.38 grams of calcium carbide reacts with water in the following chemical reaction. Calcium carbide plus water gives us calcium hydroxide plus this gas here, which is called acetylene. This is actually the chemical reaction that we did in class during our reactions unit to study combustion. Acetylene is a combustible gas, and we studied that. So acetylene is one of the products formed, and we see here that 0.77 grams is yielded from the 2.38 grams of calcium carbide. Okay, so first part of the question here asks us what was the theoretical yield of acetylene. That's basically just a stoichiometry question, so this shouldn't be anything new for you guys at this point. So we're going to take our 2.38 grams of calcium carbide and use stoichiometry to find out how much acetylene should have been yielded. So we're just going to first figure out the molar mass of calcium carbide. Okay, and so that's going to be 40.08 plus 2 times for carbon, it's 12.01, and this is all in grams per mole. Okay, so that's the mass, molar mass of calcium carbide, and in total that works out to 64.1 grams per mole. Okay, next, following stoichiometry principles, guidelines, we're going to calculate the number of moles of calcium carbide. Okay, so that's going to be our 2.38 grams divided by the molar mass, which we just calculated here, 64.1 grams per mole. Okay, and that gives us 0.0371 moles. Notice I'm keeping 3 significant digits at least, because we have, okay, over here we've got 2 significant digits, here we've got 3, so we need to keep at least 2 significant digits throughout the calculation. Okay, so we've got that many moles of calcium carbide. The next step is to find out how much acetylene would have been yielded from that. So, number of moles of C2H2, that's the acetylene, that's going to be equal to our calcium carbide number of moles times the mole ratio. So the mole ratio of acetylene to calcium carbide. Turns out that ratio is 1/1, so that doesn't change the number of moles at all. So we've got 0.0371 moles of acetylene. Okay, knowing that we've got that many moles of acetylene, we can easily calculate the number of grams of acetylene that were produced. So the mass of C2H2 is equal to 0.0371 moles times the molar mass of acetylene. Okay, so let's put together that information. That's going to be 2 times mass of carbon, 12.01, plus 2 times the mass of hydrogen, 1.01, and that was in grams per mole. Okay, and that works out to be 0.966 grams. That's our answer to part A of the question. okay, was what was the theoretical yield of acetylene? So based on these molar ratios, based on the fact that we had 2.38 grams of calcium carbide as the reactant, we should make 0.966 grams of acetylene. Okay, now it says that acetylene was produced and it's 0.77 grams that were yielded. So part B, what was the percentage yield of acetylene? We'll calculate that now. Just give a little more space. Okay, so percent yield is equal to the actual amount of material from your lab divided by the theoretical amount of material that you calculated using stoichiometry, and you multiply that by 100%. So the actual amount we're told is 0.77 grams. So 0.77 grams, and we'll divide that by the theoretical amount, which we calculated here, and multiply that by 100%. And that gives us, rounding to two significant digits, 80%. So the percent yield of this reaction was 80%. We know that because we got only 0.77 grams when we were expecting to get 0.966 grams. So we received less mass of acetylene than we were expecting to. It was 80% less, and so that's our percent yield.